Hello, and thanks for using TickBoom. I had a student send me this question through today, which you may happen to notice is Christmas Day. So props and kudos to that student for being so diligent as to be thinking about their math study on Christmas Day. I thought what better way to bide the time between Christmas lunch and Christmas dinner than to take a look and see if I could help. So the question says to prove that 1 cubed plus 3 cubed plus 5 cubed plus all the way up to 2n minus 1 cubed is equal to n squared bracket 2 to the n squared minus 1 for all integers n greater than or equal to 1. Now, this is a classic induction question where proof by induction will be able to help us. The student knew that. They were just struggling a little bit with the algebra, most likely at step 3, where you have to prove true for n is equal to k plus 1. So let's jump in and take a look. So we're being asked to prove that 1 cubed plus 2 cubed, 1 cubed plus 3 cubed plus 5 cubed plus all the way up to 2n minus 1 cubed. So basically just odd numbers, cubing odd numbers and adding them up. That will be equal to n squared 2 to the 2n squared minus 1 for integers n greater than or equal to 1. So as I mentioned, we'll use induction. So step 1 will be to show that this is true for n is equal to 1. So in that case, our left-hand side will be simply 1 cubed, which equals 1. Our right-hand side would equal 1 squared times 2 times 1 squared minus 1, which would equal 1 times 2 minus 1, which equals 1 times 1, which equals 1. So therefore, the left-hand side does equal to the right-hand side, which means it's true for n is equal to 1. Alright, step 2, we assume that this is true for n is equal to k. So what we mean by that is that 1 cubed plus 3 cubed plus 5 cubed plus all the way up to 2k minus 1 cubed will be equal to k squared 2k squared minus 1. And now step 3, which is where the hard work really is to show true for n is equal to k plus 1. So essentially we'll kind of look at the left-hand side, insert k plus 1, see what we get. Look at the right-hand side, insert k plus 1, see what we get. Often the tricky bit is to go, well, which one should I do first? I'm going to pick the right-hand side to do first because it looks like the simpler of the two. See what we get when we insert k plus 1, and then do it for the left-hand side and see if I can get to the same destination. So let's take a look at the right-hand side. So at n is equal to k plus 1, we would get k plus 1 squared times 2 bracket k plus 1 squared minus 1, which would be, let's expand this, first one squared plus twice the product plus last one squared times 2, and then the same expansion, k first one squared plus twice the product plus last one squared minus 1, which will give us k squared plus 2k plus 1 times 2k squared plus 4k plus, this will become 2 minus 1, so 2 minus 1 is 1. Now if I expand this, I'll get 2k to the 4 plus 4k cubed plus k squared plus 4k cubed plus 8 k squared plus 2k plus 2k squared plus 4k plus 1. So let's bring our terms together. So we've got 1 power of 4, so 2k to the 4. That's done. In terms of our cubes, we've got this one and this one. So that's going to be 8k cubed plus, we've got 1k squared plus 8k squared is 9k squared. Plus another 2 is 11k squared. And then we've got 2k plus 4k is 6k. And then just our plus 1 at the end. So that is where we get to with our right hand side. So the question becomes, if I put in k plus 1 into the left hand side, do I get to this same place? If I do, then the induction will be complete. So our left hand side will be equal to 1 cubed plus 3 cubed plus 5 cubed plus all the way up to 2 bracket k plus 1 minus 1 cubed, which I can write as 1 cubed plus 3 cubed plus 5 cubed plus, and here we'll get 2k plus 2 minus 1 is plus 1 cubed. And I think what I'm about to do now is maybe the step that might not jump out as being obvious, but is critical. And it's about linking up what we have with k plus 1 to what we had assumed with n is equal to k. And what I'm going to do is simply write in the second last term. That's often a helpful thing to try and do, because here we've just added one extra term. So if you write the last two terms, chances are you're going to end up seeing something that you assume to be true in step 2. So what I'll do is I'll write that as 1 cubed plus 3 cubed plus 5 cubed plus... Now what's the term before this? We're always dealing with odd numbers, so I need to go 2 numbers before this. So that's going to be 2k plus 1 minus 2, or 2k minus 1 cubed plus 2k plus 1 cubed. And notice this bit here is what we had made our assumption about in step 2. Now I might have to just turn over at this point, but what I can therefore say is that our left hand side is equal to what we'd assumed in part 2, which we can say is k squared times 2k squared minus 1 plus the final term 2k plus 1 cubed. Plus 1 cubed. So let's expand this and see if we get to this result here, what we got for the right hand side. So that's going to be equal to 2k to the 4 minus k squared plus, and this I'll expand as 2k plus 1 times 2k plus 1 squared. So we'll get 2k to the 4 minus k squared plus 2k plus 1 times the first one squared plus twice the product plus the last one squared. So 2k to the 4 minus k squared plus, and let's expand this now, so 8k cubed plus 8k squared plus 2k plus 4k squared plus 4k plus 1. So we've got our 1 power to the 4 here, so that's going to be 2k to the 4. Our k cubes are an 8k cubed and no others, so plus 8k cubed. Our k squared is minus 1 plus 8 would be 7, plus 4 would be 11. Our k's are 2 plus 4 is 6, and then our plus 1 at the end. So 2k to the 4 plus 8k cubed plus 11k squared plus 6k plus 1. That is the right-hand side that we had expanded. So therefore, true for n is equal to k plus 1. So now we can conclude that by induction, 1 cubed plus 3 cubed plus 5 cubed plus all the way up to 2n minus 1 cubed, the summing of all our odd numbers is equal to n squared bracket 2n squared minus 1 for the n greater than or equal to 1, n integers greater than or equal to 1. So that's it. That's the induction. So I can see how, again, most of the time it's step 3 where things can get tricky. Here, it was really just about expanding both the right and left-hand side and being careful with the algebra. And I think this is the key point where when you're expanding your left-hand side, thinking to write the last 2 terms, because that's often what can help you get your link between step 3 and step 2. So hopefully you found that helpful. Merry Christmas and tick boom.